demonstrate it, but we're not sure if it's going to work, so I've got a video as well. But we'll see what happens. Hello, clicker, work. Right, that's me. So you can get me on Twitter, @TechGirl, or Mandy Waite on Google+. That's my Twitter handle's on every slide, so if you want to tweet questions or anything like that, please do. I will be around as well through lunch break. And so anybody knows what this is? This is a data center. This is a data center in Iowa, Council Bluffs, Iowa, in the US. And this is what our engineers run their stuff on, right? But I'm going to have to kind of speed this up. It's a very short talk. So how do we make this kind of computing infrastructure, these resources, available to our engineers, our software engineers, and our developers? That's the secret. We don't want them to have to worry about identifying a machine in one of these racks on which they're going to run their stuff. We don't want them to have to SFTP a binary over and then stand that binary up by SSH into the machine. Maybe do that across multiple machines because they want to scale the thing they're running, the service they're running. So what do? They do this. They create a configuration file. This one's called Halliwell. So this is Halliwell for the data center. I'd love to be able to run this one day. And we have those things we saw in the data center split into cells. It's a cluster, but we also divide them into cells of tens of thousands of machines. And in order to run something, you don't specify a machine, you specify a cell. Right? So we're saying, I want to run it in this cell. So cell equals IC is my binary. It's probably a fat binary, statically linked. It includes a web server as well. We statically link nearly everything. And it runs in a container as well. So it has a very lightweight container wrapper around it. And we've been doing this for a long time. So when Docker came along and everybody started talking about containers, we got really excited. Because, oh, look, we did that already. So 2 billion containers a week, apparently. We can specify some arguments. We can specify resource requirements, how much RAM, how much disk, how much CPU that job will have, or each individual task for that job will have. And we can say how many replicas of it we want, say in this case 5, or maybe for Google scale, we want 10,000 of them. So I could do this myself as an engineer at Google. I could just create this configuration file, push it out, and I would have 10,000 of these things running. And this takes about 2 minutes, 40 seconds to ramp up. We do slow start it. We have to move all of that data around. The binary is about 50 megabytes, and so this works out about 2 gigabits per second of moving around data. And so we do slow start it, and after 2 minutes, 40 seconds, we have 100 running. And so what just happened, really? What did just happen? We've taken our binary, well, we built our binary using our internal build system, which is now available on GitHub, called Bazel, open sourced. So if you go to GitHub, Bazel, B-A-Z-E-L, not Z, B-A-Z-E-L. Sorry, I get mixed up. Canada's the worst. I go to Canada, it's like they speak British. And it's like, oh, wow, okay, they say route instead of route. It's fantastic. And so what happens is the binary is copied over to local storage for the cell, and we push the configuration file. That gets stored into a Borg master. So Borg is our scheduler. We have 1 Borg per cluster, per cell, sorry. So we have that Borg master, which is highly replicated. We have a persistent Paxos-based store for storing stuff. And then at some point, a scheduler comes along and says, what should the state of this cell be? Oh, look, there's 10,000 of these things that should be running that aren't running. So let's fix that. And so they go ahead and fix it. And they instruct individual machines, which are these blue boxes at the bottom, that are running Borglets, a control system that runs on each node, that manages what's running on each node. And they say, run this for me. And so each machine that's running it, we have a plan. We've created a plan for where we're going to run these. That's what the scheduler does. And they will go and pull in the binary from the storage and start running it. And eventually we get that. Yay. There's not quite 10,000 of them there. So. But that's important. So there isn't 10,000 of them. There's like, if we look later, there's 9,993 of them running. Because we're running 10,000, it doesn't really matter that much if we have 7 or so missing. So this is kind of like what we're trying to get to, 10,000. But there are various reasons why we won't have 10,000 at any given time. And we're going to look into that very quickly. I'm going to keep a track of the time. So one of the reasons is failures, things that fail. And failures are nothing wrong. There's nothing wrong with failures. It's not like we run around panicking. Well, we do sometimes, but not all the time. So these failures can be for a variety of reasons. And we can see prod at the top, which is that blue bar over here, and the grey bar, which is non-prod. Non-prod is things like map reduces, batch jobs, those kind of things that we want to run, we want to finish at some point, but we don't really care when. They have a much lower priority, and they use resources that may not always be available. They may be preempted and kicked off. And so they get preempted quite often, and that's that big grey bar at the bottom. That doesn't happen for prod. Those things just run, and they're high priority. They don't get evicted for any reason at all. And we have other things as well. We're not going to talk about them. But ultimately, this is evictions per task week, and that would ultimately account for the 7 that we saw on the previous slide that were missing. So we never quite get to 10,000, because some of them are being kicked off machines and rescheduled. These things will always be rescheduled and run eventually, but they're not high priority. And so another thing is efficiency. How do we make things efficient in our network? And the first one is we specify resources. We saw that in the configuration file already. And how much memory, how much CPU. And that's how much the developer thinks they're going to need for that job. And the reality is different. When we're running that, we see something extremely different. We see this curve here, usage, actual resource consumption. But we can actually predict, based on complicated algorithms, how much it's likely to use at any given time. And we can create this reservation. And the reservation is fairly dynamic, but it does say, this is what we expect this to use. And what we can then do is say, this stuff here in the green, from what they requested and what's actually reserved for them, is now free to be used for something else. And we can run those low priority batch jobs, those map reducers in this green space here. So that's great, because now we're reusing resources that would not have been available for us. And the next one, in terms of efficiency, we look at this. This is a single machine, this black bar here. This is virtual machines, compute engine virtual machines. Compute engine is our infrastructure as a service offering. And a virtual machine in Google is actually a container. It's actually something running as a job that we saw earlier. It's not actually, well, virtual machines are virtual anyway, right? So it doesn't matter how virtual they are. So this is one machine, this bar here. And these are lots and lots and lots and lots and lots of machines. July 2014, this was taken. And that raises some interesting observations. One is efficiency and available resources. So if we look at these two here, we have memory at the bottom, CPU at the top. We can see that we have spare CPU where we have spare memory. That's great. We can use that for running other jobs. This one is not so good though, because we have memory here, CPU at the top, and we can see we have spare memory, but we have no spare CPU cores on those machines. So we can't run anything more on them, but we're wasting that memory. Okay, that's called resource stranding. So those resources down here are no longer available to us because we're maxed out on CPU. And so ultimately, let's think about our cell as being one big machine. That's what we think about as a machine. And so therefore, the individual machines, the virtual machines or bare metal servers, become just a resource boundary, a boundary for CPU and memory. And at some point that we're going to go away and we won't care about these boundaries. But at the moment, a virtual machine or a physical machine acts as a resource boundary. It has X amount of CPU and X amount of memory. So it's down to a scheduler to actually work out some puzzles and actually schedule stuff on those machines. And machines have shapes. So this is a 8 gigabyte 4-core machine, so 2 gigabytes per core, 4 gigabytes per core, 1 gigabyte per core. And then we have workload shapes as well. So these workloads have shapes. And 1 gigabyte, 1 core, 3.5 gigabyte, 1 core. The scale is kind of like complicated, but I just kind of worked that out yesterday when I wrote this slide. And so that looks like this. We can schedule a job, 2.5 gigabytes, 1 core job on this machine over here. But now we've got lots of spare resources. So we can move it over to this one. I'd love to do better animations, but I do have fun with them. So in this case, we're now running on a machine where we have 1 core available to us and 5.5 gigabytes of RAM. That's pretty good. We can actually run another job there. So we can run that job there. So this one uses, 6 gigabytes. Should be 5. That is a typo. That is not overcommit. I was going to talk about overcommit, but I'm not going to. But we could talk about overcommit later. No, maybe outside. So overcommit is great. But this uses the other core, and it uses all of the rest of the available memory. We may have some headroom. Bin packing always comes with overhead. And so this is resource stranding. We have our job that uses one core, 2.5 gigabytes of RAM. It's used all of the CPU, there's all of that memory left available. And this can work the opposite as well. So we can have all of the memory consumed and CPU cores not used. And that's probably more critical. But if we move that job to a 2-core machine, we now have that RAM available to us, and we have 1 core, and we can run that second job. So that's called bin packing. So basically, anybody familiar with the knapsack problem? Yeah, the knapsack problem. You probably learned it in your CS class at university and then forgot it straight away. Like bins, you have bins and weights, and you have to put them in. What's the most efficient way? Different algorithms to use. So bin packing is extremely important, and that's part of one of the efficiencies that we have within Google, is effectively bin packing this stuff so that we have the right Tetris puzzle shapes fitting on the right machines. And so some observations. Some of these I haven't covered. I've had to cut lots of slides, but we scavenge unused allocations, as you saw. That's big green space is stuff we use for our batch jobs. Effective prioritization. Prioritization is massively important. We have to get that right, and we spend a long time getting it right. Sharing resources and overcommit I've not really covered, and also smarter scheduling. So this is the whole bin packing, understanding where we can schedule a job. So ultimately, the data is just one big system, a cell in our case, and the machine is just a resource boundary. And I haven't really mentioned it. Everything's run on containers that I have mentioned, but containers make everyone more productive. And that includes us as well. How many of you have heard of Kubernetes? Everybody? Yay. So that's good, because just in case some of you haven't, this is what Kubernetes is. It's a Greek word that's very hard to say. If anybody wants some lessons on how to say Kubernetes, you can catch me up later. Sorry. People do struggle with saying Kubernetes, particularly in different languages. It's a very Japanese word, Kubernetes. It's with a su on the end. So it's an orchestrator for containers, Docker containers, ultimately Rocket containers, ultimately our standard container format, which we will eventually have, which Docker will be one implementation of, and which Rocket will be one implementation of. So you'll be able to run containers on this, regardless of what type of container they are. It supports many cloud environments. It supports all of the major cloud providers, but again, it varies depending on which one you go to. It supports things like Red Hat. It's supported by Mesosphere. It's open source and is written in Go. And ultimately, what we really care about is managing applications, not having to worry about machines. We want a big cluster of machines and just deploy our stuff on it. This is the developer view of Kubernetes. And again, I don't have a huge amount of time to go into this. So it looks very similar to what we had before. We have a scheduler, we have a master. It's not highly replicated currently. At the moment, high replication is still waiting to happen. It will eventually. And there are strategies to get around that. We host the master for you on Google Container Engine, which is a production implementation of Kubernetes. But we also have machines here. This is our cluster, each one running a kubelet instead of a borglet. And we have an API server, which is extremely important, which we'll use shortly if the Wi-Fi works. And so this is a very quick run-through of Kubernetes. Who hasn't heard of Kubernetes? Hey, nobody. I'll just go through this. You know what all this is, right? Do I need to explain that? No, I don't. Oh, I should do really. Pods are the scheduling unit of Kubernetes. A pod can contain a container, multiple containers, a volume and containers. And generally, if you have multiple containers, that's because it makes sense for them to run on the same machine, co-located. Maybe you think of a pod as a logical host on which you would run 2 containers, 3 containers that make sense to run together. These things are completely ephemeral. They can come and go as they please. They don't store state. They may store state on an external volume, but they don't have state internally. And they have labels. Labels are big in Kubernetes. It's the single unit of single grouping mechanism in Kubernetes. They can have many labels. Label is basically arbitrary metadata. So you say version equals v1, type equals fe. It means something to you. It doesn't mean anything to Kubernetes. although there are some labels that mean things for Kubernetes. Replication controllers, like our scheduler, are responsible for maintaining state. So we say to them, this is a template for a pod. We want 2 of these. This is the label selector to use. Make sure this state is always the case. And when you fire up the replication controller, it looks and says, oh, I should have 2 of these pods. I don't have them. I will create them. So it creates them, and then it constantly monitors to make sure there's always 2 of them running at any given time. And then we have a service, and the service effectively acts as an endpoint that other services can connect to consume this service that's behind in the pods. So it's like a load balancer effectively, but it does provide an endpoint. It could be an external endpoint in the cloud, which clients can connect to, or it could be an internal endpoint, which other services can talk to. Then you can do this kind of canary situation where you have another replication controller with another pod with a slightly different label, version equals v2, and type equals FE. So again, the constituency of this service is type equals FE, and all 3 of these have it. So all 3 of these pods will be constituents of this service. And this replication controller is responsible for 1 pod. But it means we now have 33% of our traffic going to our new version and 66% going to our old versions. So we can canary that effectively. And later on, we can actually roll out an update to update everything so that all of the pods are the same. And I'm going to skim through this. When you create a replication controller, you do pretty much the same as what we do internally at Google, including memory and CPU limits. And so visualizing Kubernetes, we'll go into a demo, see if it works. Oh, God, it's so small. Was that? Okay. Go. All right, okay. So, first thing to do is look at this. We have a visualization of what this all looks like. We have a service. This is a service. The green ones are services. And this has 2 IP addresses. And I created this early because it takes a while to set up the external IP address. So the bottom one is actually an external IP address. And we can actually attach to that remotely. This is a real living service. And I need to check to see if we actually have connectivity by going into the console and seeing if we're talking to the API. Oh, why is it scrolling like that? I hate that scroll bar. It just disappears and you have to kind of chase it. Chase the... Ah, right, okay. So let's see if it works. Yeah, it's working. Okay, so good. All right, so now this is talking to the API on our cluster. We have a cluster. This is a container engine cluster, and it has some nodes. Yes, 2 nodes. And so this is our visualization. What we want to do is actually create some pods. The first thing we're going to do is create a MySQL pod, and we're going to do that using the kubectl command. I feel sorry for Radek over there because he's seen this demonstration so many times. And we can just specify a directory here, and it will create both the service and the pod for us. And let's get rid of that. We don't need that. So now we have a service up the top there and a pod. And this is using JS Plum. Some reordering happens when we create new things. So MySQL, it was yellow. It was pending. So it was actually being set up. And then it went white. That means it's running. So we've gone from pending state, yellow, to white, which is the more grey, which is the running state. And then we can do the same for, I'll move this up. We can do the same for Memcache. So we want Memcache as well. I'm running through this. But there are some versions of this on YouTube. So now we have Memcache and MySQL. We have 1 pod, and we have 1 service per each. So now let's create a front end. These are our PHP pods. So this is a basically traditional PHP LAMP stack. We're going to create a front-end service. No, front-end service is already created. We're going to create a replication controller. And we're going to use v1. So we have a version 1 of this replication controller. And that's going to create a front-end replication controller, and it's responsible for maintaining the state of these 2 pods. When it came up, it said, oh, there should be 2 pods. There aren't 2 pods. Let me create them for you. And it created them. And we can scale that if we want to. And I'm going to try and make this quick. I can scale that to 6 very easily. So if we want more pods, we can say scale it. So you see they're all yellow currently, and they'll all change to grey. That's good. And we'll scale that back down. The next thing we'll do is we'll roll out an update. And our update will involve updating to something that's using a different image, different Docker image, which is stored in a container repository. And we should be able to see. Have I got it here? I have got it here. If we can connect. Connect, please connect. All right, so let's just go back to the demo. So what I'm going to do now is I'm going to actually replace this replication controller with a new version of our pod template. And it's going to create new pods, and it's going to roll the update out, changing each one of the existing pods to the new one effectively until we have all of the ones at the new version. So to do that, I need to do a rolling update. And I have one called Big, and Big effectively is one that has a requirement to have 1 CPU per pod. We only have 4 CPUs, so this could be a bit of a problem. So let's try this. And you'll see it creates a new replication controller, then it will create a new pod, which is the new version. This is a big pod. And then it will remove one of the 1.0 pods, ultimately. And then it will create another one of the big pods. One big pod, big pod, there's big pod. Then it will try to remove the other 1.0 pod. Now, if something's stuck here, we have the big one's not going to come out of pending. I'm pretty sure it's not going to come out of pending. We don't have the resources to run this pod. We've said we want 1 CPU per pod. We have 1 of them running. Well, we haven't even got 1 of them running. There's not enough resources because we have all of these other pods and services running already, all of this stuff. We don't have enough room to run this pod. So really what we need to do is go into container engine and compute engine, in this case, instance groups. This is a group of instances that represent our cluster. And we can go in here and we can click Edit Group. You see we have 2 instances currently, and I'm going to change that to 3, and we'll see what happens. So that's creating that instance, and we'll come back to that shortly. We'll wrap up the slides because timing is really important. This stuff I can't really go into, but this is how we schedule stuff on nodes. We have resources, we have disks, and we have labels. We have scheduling capabilities. You can read about all of these on the slides, which are on our website currently on speakerdeck.com. Can't go through these. Kubernetes is 1.0 as of mid-July, and it's won several awards. We have at Google a product version of this called Google Container Engine, which is effectively hosted Kubernetes. We manage the master for you. You don't get to see the master at all. We take it away, and we make sure it's always up, because we don't have real high availability for Kubernetes currently. So you basically put your master in our hands, and we'll look after it for you, like a puppy. And then we have Container Engine, which is Kubernetes version 1 managed. It manages all of the uptime, manages the updates. You can cluster resize like we just did. It has centralized login, all going into our cloud monitoring, and also cloud VPN support. And there's so much more I'd love to tell you, but I don't really have the time. So let's go back into this and see what's happened. Oh, it hasn't done it yet. Come on, come on, come on, do it. Do it. It worked earlier. So basically, what I would do now, but I'm going to pack up because I don't want to hold anybody else up. I can look at the events. I'm not sure if you can see that. Oh, get events. Okay, interesting. So basically, normally this would say pods fit resources is the problem. It doesn't have the resources available in the cluster to actually schedule this. But anyway, so come and find me outside for dinner and ask me questions. Tweet me questions as well. I will always do my best to answer your questions on Twitter or anything else. If you want to chat privately, I can give you my email address as well, and we can talk on email. But yeah, definitely check Kubernetes out. It will change your life. I keep telling people this. In a couple of years' time, I'll come back and you'll say, yes, you were right. It changed everything. I'm out of a job now. No, not that, definitely. Right, thank you very much. Cheers.